All right, guys. So this video is going to cover the rest of the trends. So we're still in 1-3 periodic trends. So the previous video went over, just in general that we want to make sure that we're being able to explain why the trend is what it is. So why does this increase going that way or decrease going that way, and why does it increase or decrease going down the periodic table? We want to be able to explain the trend using structure. So how many protons are in the nucleus, so nuclear charge, and how many electrons are in the cloud and where they are within the cloud. Are they closer energy level? Are they further away out energy level? How much shielding is going on? And it really comes down to Coulomb's law, right? Charge of the nucleus, the greater the charge, the stronger the attraction to the nucleus, but the higher the energy level, the further away they are from the nucleus, the more shielding there is between valence electrons and core electrons, the weaker the attraction. So we have all these things, but it all boils down to opposites attracting and like charges repelling, right? So that's the whole idea. So now let's get into the rest of the trends. All right. Now the next trend that we want to talk about is really important. Electronegativity. Okay. So the definition is like the ability or the tendency that an atom has to attract electrons towards itself. Okay. So the pull an atom has of electrons, and the pull is the nucleus. How well can the nucleus attract other electrons, right? And the two main things there are, well, the more protons I have, the stronger the attraction I would have. But then you have the electrons that atom already has shielding that outside electron. So you have this outside electron that the nucleus is trying to attract. It's shielded by the electrons the atom already has, right? And then, so the more electrons that atom already has, the less it's able to attract it, right? But the more protons it has, the greater the ability it has to attract it, right? So it's this balancing act, okay? So the thing to remember about the periodic trend, I don't know if you can see these numbers or if it's illegible here, but notice these are electronegativity values. Notice like krypton and xenon actually are given an electronegativity value. Don't worry about that. Just ignore the noble gases when it comes to electronegativity. What you want to remember is fluorine is the most electronegative. Okay, and you don't have to remember its value. Just remember fluorine is the most. And between oxygen and chlorine, oxygen is the second most. Okay, and that's the reason why we call losing electrons oxidation, is because back in the day when we were studying what do metals do when they react with oxygen, they always lost electrons to oxygen, and so we called it oxidation. But now, just in general, losing electrons is oxidized, right? But the reason why oxygen is so good at taking electrons is because it has a very high electronegativity. Now, it's not as good as fluorine. Fluorine's the most, but oxygen is the second most, okay? When are you going to invoke electronegativity? When you're talking about polarity, okay? So when you're talking about polar covalent bonds, you will never, never, ever, ever, ever use electronegativity to explain the strengths of ionic bonds, right? So if you're asked why does sodium fluoride have a stronger bond than sodium chloride, you would not say because fluorine is more electronegative than chlorine. Electronegativity has nothing to do with ionic. Once it's ionic, the transfer of electrons has occurred. It's not about unequal sharing. It's about the radius of the ions. So the answer to this question, why is this a stronger bond than that? It's because fluoride is smaller than chloride. And so because sodium and fluoride can get closer to each other than sodium and chloride, the sodium fluoride bond is stronger, right? Okay. All right, so that's, that happens a lot. A lot of people want to use electronegativity to explain ionic bonds. You will use electronegativity to explain covalent bonds, okay? All right, so we know electronegativity increases going this way. Fluorine's the most, francium would be the least, right? And we wouldn't worry about the noble gases, okay? Now, why is fluorine so good at attracting electrons? Because it has one of the smaller radius, okay? So that means it has very low shielding. So, and it has a +9 nucleus. So all of these elements in row 2 have very little shielding, okay? Because they don't have that many electrons. They only have 2 energy levels worth of electrons. But since fluorine has the most protons of all of them, not including neon, it can pull that electron closer to it than any of the other ones. So that's why fluorine is the strongest in terms of electronegativity. Okay. So if we're talking about covalent bonds, electronegativity is invoked when you're talking about how polar the bond is. So what is a polar covalent bond? It's sharing of electrons, but it's unequal sharing of electrons. And the uneven or unequal sharing of electrons is a result of electronegativity difference, right? If we're going to share electrons, but I have a stronger ability of pulling those electrons closer to me, then we're not going to share them equally. The electrons are going to spend more time around my nucleus than they are your nucleus. So I'm going to have those electrons more than you are. So I'm going to end up becoming negatively charged, and you're going to end up becoming positively charged. And having those oppositely charged poles, we call those dipoles to the bond, is what makes a bond polar. And it's all due to the electronegativity difference. What you need to understand is the bigger the difference in electronegativity, the more polar the bond. And the more polar the bond, that's going to mean the stronger the bond. It's also going to mean the higher the negative charge of the dipole of the negative side of the bond, the higher the positive dipole of the positive side of the bond, and then the stronger the dipole-dipole interactions when we start talking about intermolecular forces. So electronegativity is going to build. We're going to use electronegativity to explain the difference in strengths of polar bonds. Then we're going to use it to explain the magnitude of the dipole. So how negative this one is, how positive that one is. And then when we get to intermolecular forces, I can ask you, if I ask you, why is this dipole-dipole interaction stronger than that dipole-dipole interaction? The reason is because, this bond has a bigger difference in electronegativity, making it more polar. That means this dipole is more negative than that dipole. That means the dipole-dipole interaction that's going to occur is going to end up being stronger. So a lot of stuff going on when we get to electronegativity. But let's look, so here are bond energies. Notice they're in kilojoules per mole. So let's look, why is the CF bond stronger than the CCl bond? And it comes down to Coulomb's law, but we know that CF is going to be more polar than CCl. Why? Because there's a bigger electronegativity difference. So 4 minus 2.5 versus 3 minus 2.5, right? I know that the CF bond has a greater difference in electronegativity, so it's going to be more polar. More polar means stronger, okay? And the other reason is because I know that fluorine is smaller than chlorine, so I know the length of this bond is shorter than the length of that bond, right? So, I type CF with the same font that I typed CCl, but on paper, this looks exactly the same as that. But we have to know, we go back to the atomic radius trend, we have to know that fluorine is smaller than chlorine. So this nucleus is going to be able to get closer to that nucleus. So the distance between the bond here and the distance between the bond here, this is shorter. And the closer they can get to each other, the stronger the attraction. And then also, we know we have a higher negative charge on the fluorine and a higher positive charge on the carbon because we know we have a bigger electronegativity difference. All right? So some of you might be asking what a dipole is. Well, if I know that this bond is polar, and I should know that chlorine is more electronegative than hydrogen, okay? That means they're sharing those 2 electrons there, but it's uneven sharing. And so the element that has the greater electronegativity is going to get a negative charge, and the one that has a lower electronegativity is going to get a positive charge. This little symbol here means a partial charge because it wasn't a complete transfer. If the hydrogen lost the electron and the chlorine gained the electron, it wouldn't say partial negative, this would say -1, and this would say +1. But since it's not a complete transfer, it's just an unequal sharing of electrons, this has a partial negative and this has a partial positive. Okay, well, this partial negative charge on this atom is called the negative dipole, and this is called the positive dipole. Okay, so when you have polar bonds, you get a negative dipole and you get a positive dipole. Okay, and then this interaction between the negative dipole of this molecule and the positive dipole of that molecule, that interaction right there, this dashed line is representing a dipole-dipole interaction. Okay. All right. So here, I have a dipole-dipole interaction illustrated in an HCl molecule. And here I have a dipole-dipole interaction here in an HF molecule. What's the difference? Well, that's when it comes to all the trends that we need to know. Okay. I have to know that this dipole-dipole interaction is stronger than that dipole-dipole interaction. How do I know? They both are illustrated the exact same way on my piece of paper. Well, two things. You know that fluorine is more electronegative than chlorine. So the difference between this polar bond is more polar than that polar bond. What does that mean? It means this partial negative is higher in magnitude than that partial negative. It means that this partial positive is higher in magnitude than that partial positive. So this interaction is going to be stronger because this positive is higher than that positive, and this negative is higher than that negative. So that interaction is not going to be as strong as this interaction. Okay. The other reason it's stronger is because fluorine is smaller than chlorine. So these molecules are actually going to be able to get closer to each other. So not only is the charge higher than that charge, but they're actually going to be closer to each other. And so that's going to strengthen the attraction. Now, that's not illustrated here. That's stuff we have to know based on the trends. That's the stuff we have to remember. Okay? Because when we illustrate it, it's all going to look the same, but I have to look at this and go, oh, well, this interaction is stronger than that interaction. Why? Coulomb's law. But really, if you want to boil it down, because I know that this charge, this positive is greater than that positive, and this negative is greater than that negative, because I know that the electronegativity difference between this bond and that bond is greater. And then I know that F is smaller than Cl, so not only is that interaction stronger because these charges are higher, but also I know the distance between this molecule and this molecule is shorter than this molecule and that molecule, right? And it all comes down to trends and understanding what they actually mean and how we can apply them, all right? All right. So electron affinity, I'm not going to spend much time on. You just really want to know the definition and the trend. It has the same exact trend as electronegativity. So fluorine has the highest and francium would have the lowest. But the definition is it's the amount of energy released when an atom gains an electron. So think of it, it's kind of like the opposite of ionization energy. Ionization energy is the amount of energy required to remove an electron. And it always requires energy to remove an electron. So it's always endothermic. Electron affinity is actually the amount of energy that gets released when an atom gains an electron. And so electron affinity is an exothermic process usually, because when you gain electrons, you actually release energy normally if it stabilizes you. But when you lose electrons, all electrons, even metals, the metals are still, the metal nucleuses are still attracted to their valence electrons. They're just not as strongly attracted, but it's still like, even though francium has the lowest ionization energy, it still requires some amount of energy to remove an electron from francium, right? So ionization is always endothermic, but electron affinity, when we say fluorine has the highest electron affinity, what we're saying is fluorine loses the most energy when it gains an electron. So losing energy means most stability to gain, right? So fluorine has the most stability to gain. What does that mean? It means it loses the most energy when it gains that one electron to satisfy its octet rule, right? All right, and that's basically all you need to know. It probably won't ever show up on the AP exam, okay? But one that will is ionic radius. So understand that ionic radius and atomic radius don't have the same trend, okay? They do have the same trend going down the periodic table, right? If we looked at ions get bigger as you go down, okay? But what I want you to notice is like lithium 1 plus is actually going to end up being smaller than helium. Beryllium 2 plus is going to be smaller than lithium, right? But notice, right, look at here. Look at magnesium 2 plus is smaller than fluoride 1 minus, all right? So a couple things to understand. If you lose electrons, your cloud's going to get smaller. So cations are always smaller than what they were when they were neutral. So I know sodium 1 plus is going to be smaller than just neutral sodium. But the reason that is because sodium 1 plus lost its valence electron. Now it has the same number of electrons as neon. It has the same electron configuration as neon, but it has one more proton than neon. So sodium 1 plus is going to be smaller than neutral neon because it has the same number of electrons, but one more proton in the nucleus. It's going to be able to attract it further, okay? The other thing to understand is if you gain electrons, your cloud's going to get bigger, so you're going to get a bigger radius. So anions always end up being bigger than what they were as neutral atoms, okay? But the thing you really want to focus on is things that are isoelectronic. So comparing two different things, maybe two different ions, or comparing an ion to the size of a noble gas when they have the same electron configuration. So that's all isoelectronic means. It means same electron configuration. So when you have the same number of electrons, it's really easy. When you have the same number of electrons, the atom or the ion that has more protons in the nucleus is going to be smaller because it's going to be able to attract those electrons closer to it. And the one with less protons in the nucleus is going to end up being bigger, okay? So like in an isoelectronic series, so here's an example. N3 minus, O2 minus, F1 minus, they all have the same electron configuration as neon. Sodium 1 plus, magnesium 2 plus, aluminum 3 plus, and we'll go silicon 4 plus, all of those would have the same electron configuration as neon. So all of these things have the same electron configuration as neon, but of all of those, silicon 4 plus would be the smallest, and N3 minus would be the biggest. So it would go from biggest down to smallest. Okay, so notice it's not within one row. All right, so it's really like the nonmetals of the previous row and the metals of the next row. The nonmetals are bigger, the metals are smaller because the metals of the next row, when we're talking about them in terms of ions, have more protons than the nonmetals of the previous row, okay? All right, and then so the last two is just like metallic reactivity or metallic character. So just remember, you can say all these different characteristics of metals. They're good conductors, they're malleable, they're ductile, they conduct electricity as a solid, but not when dissolved. And so whatever. You can say all these different things. The defining characteristic of a metal is that it loses electrons when it reacts, it oxidizes. So the most metallic metal is the one that has the lowest ionization, which means it's the metal that gives up electrons the easiest. So that would be francium. So as you go further down into the left towards francium, and francium's down here, but as you go this way on your periodic table, you get more metallic. Why? Because ionization energy decreases. As ionization energy decreases, as first ionization energy decreases, you become more metallic in character. Okay? It doesn't mean you become harder, or it doesn't mean you become more malleable, and it doesn't mean you become more conductive. It means you lose electrons the easiest, because that's the defining characteristic. Okay? And then non-metallic character is about gaining or sharing electrons, and the element that's the best at that is fluorine, because it's the most electronegative. So fluorine is the most electronegative, making it the most non-metallic. Francium is the most metallic because it has the lowest ionization energy. Okay, we wouldn't include the noble gases in non-metallic character trend because they don't really react. When we talk about non-metallic character, we're talking about reactivity. So we're talking about gaining or sharing electrons. And the noble gases don't like to gain. They don't like to share. They're stable already with the number of electrons they have, so they don't really form bonds. Okay? So metals form bonds by losing electrons. So the ones that lose the electrons the easiest, so lowest ionization energy, is the most metallic. And non-metals form bonds by gaining electrons or sharing them. And so the ones that are best at that are the ones with the greatest electron negativity, electronegativity. All right. All right. So these past two videos cover all the trends. And so, hopefully with what we go over in class and watching these videos as a refresher, you can finish the 1-2 assessments, the 1-3 stuff, the AP classroom concept check, and the 1-2, 1-3 Schoology assessment. Okay. So Friday into next week, we'll be starting structure of molecules. So instead of just individual atoms and ions, now we're going to talk about molecules. So like VSEPR theory, so shapes of molecules, dot structures of molecules, polarity of molecules, intermolecular forces between molecules. And guess what? It's really going to come down to Coulomb's law. Shocking. But the better you know the trends, the better you can look at something and go, oh, well, on this piece of paper, fluorine and chlorine were drawn with the same font. But understanding that, oh, when I'm looking at F, that's a smaller thing than Cl, and looking at this, that's a more electronegative than that, and understanding what that means in terms of polarity and dipoles and how close things can get to each other versus how far they have to be from each other, that will start explaining a lot of these things, and you'll be able to answer a lot of questions that AP is going to throw at you. All right, so have a good one.